Masked diffusion models have quietly become one of the most promising frameworks for generating discrete sequences like code and natural language. But they have a structural flaw that actively limits their reasoning capabilities. Every time these models denoise a sequence, they compute rich, continuous hidden states for every position, including the ones that are still masked. And then at the end of the step, they throw all of that computation away. The next denoising round starts completely fresh. We refer to this as the hard reset problem. It means the model cannot accumulate intermediate reasoning across steps, even though recurrent computation is exactly what recent research shows boosts performance on complex multi-step tasks. Today, we're going to look at a new method called learned relay representations, or relay, which fixes this by teaching diffusion models to be forward-thinking. In standard masked diffusion models, generation is an iterative process. You start with a fully masked sequence, and at each step, you unmask a fraction of the remaining positions. The transformer computes logits for every masked token, but once you commit those tokens to the sequence, the internal activations for the rest of the step are discarded. It's functionally equivalent to solving a puzzle by making a guess, checking your work, and then erasing your scratchpad before making the next guess. You lose all the contextual reasoning you built up. Relay changes this by introducing a differentiable, continuous state that gets carried forward from one denoising step to the next. Think of it as a persistent scratchpad. Instead of starting from zero, the model takes the hidden state from the previous step, processes it through a lightweight relay module, and adds it to the current token embeddings before running the next forward pass. Let's get into the mechanics. The core idea is to augment the standard inference trajectory with a hidden state, which we'll call h at step k. Given the partially masked sequence and the previous relay state, the model computes the next hidden state by feeding the sum of the embedded tokens and the projected relay state into the transformer backbone. The logits for the next step are simply read out from this new hidden state. But simply piping these states forward isn't enough. If you don't train the model to actually use them, they'll just become noise. So relay is trained end-to-end, using truncated backpropagation through time. During training, we don't sample random masked sequences. Instead, we start from a fully masked state and roll out the model step-by-step using an on-policy unmasking strategy. We teacher-force the newly revealed tokens to match the ground truth to prevent error accumulation, but we let the unmasking policy be guided by the model's own confidence scores. We then compute the cross-entropy loss over the masked positions and backpropagate through the entire rollout. This teaches the relay module to write information into the hidden state that will actually be useful for predictions several steps into the future. It's essentially training a latent chain of thought that operates across the denoising trajectory. To validate this, the authors start with a controlled environment, Sudoku Extreme. This is a perfect testbed because it requires strict constraint satisfaction, and you can measure how well the model maintains partial board legality at every intermediate step. They run a series of ablations. First, they replace the standard uniform masking with an on-policy confidence-based sampler. That gives a baseline improvement. Then they turn on the relay channel, but stop the gradients before it feeds back into the backbone. That alone causes a massive jump in accuracy. But the real breakthrough comes when they enable full truncated BPTT through the relay. The results show that BPTT explicitly teaches the relay to keep the partial board self-consistent. At the same confidence threshold, the full relay method commits more cells per forward pass while still honoring row, column, and box constraints. It reduces the total number of forward evaluations needed to solve the puzzle, shifting the entire accuracy versus latency Pareto frontier outward. The real test, though, is scaling this to state-of-the-art language models. The team adapts Fast-dLLM v2, a 1.5 billion parameter diffusion language model that uses blockwise diffusion and KV caching for efficient inference. They fine-tune it on a mixture of code and math instructions. Here's where it gets interesting. Relay isn't just compatible with existing acceleration techniques, it works alongside them. They run the two-step relay rollout only inside the active diffusion block, leaving previously decoded blocks frozen so their KV cache stays valid. The results on HumanEval and MBPP are strong. Relay outperforms standard supervised fine-tuning, pushing code completion accuracy up while cutting the number of forward evaluations by up to 32%. That's a direct translation from training methodology to inference speed. You might wonder about the training cost. Backpropagating through two steps usually doubles memory usage, but the authors profiled the GPU memory footprint on an A100. Because the peak memory is dominated by the cross-entropy backward pass through the vocabulary projection head, the relay's extra activations get released before that spike. The actual peak memory difference is less than a gigabyte. So the training overhead is minimal, but the inference gains are substantial. It's worth noting how this sits in the broader research landscape. Some approaches try to carry information across steps by augmenting discrete variables with continuous diffusion processes in the embedding space, or by passing top K predictions back as soft masks. Others, like metastate or loopholing, inject hidden states from previous steps into the current input, similar to what we'd call a stop gradient relay. But relay goes a step further. It doesn't rely on continuous diffusion relaxations, and it doesn't just inject past states as fixed conditioning. It trains the relay channel end-to-end via BPTT, so the model actively learns to optimize the latent state for future unmasking decisions. It's a purely discrete, recurrent mechanism applied to a non-autoregressive diffusion framework. So what does this mean for the future of discrete diffusion? Relay proves that the hard reset problem isn't a fundamental limitation of masked diffusion, but rather a missed opportunity for recurrent computation. By treating the denoising trajectory as a continuous computational graph, we can train models to amortize reasoning across steps. There are trade-offs, of course. The relay adds a small per-step overhead, and training requires slightly more memory and compute. But as the results show, the reduction in total forward passes more than compensates for it. The framework is also largely architecture-agnostic, which opens the door to applying this kind of forward-thinking latent propagation to image generation, molecular design, or any discrete diffusion task. If you're working with diffusion language models, this is a concrete, implementable step toward making them not just generative, but genuinely reasoning. The code for all experiments is open source, so if you want to dig into the implementation or run your own ablations, the link is in the description. Thanks for watching.